Okay, we are going to start soon. Okay, yeah, this is already. Bien, buenos días a todos, a toda la comunidad latinoamericana. Esto es la red LAFMAT, Red Latinoamericana de Física y Materia Condensada y Ciencia de Materiales. Good morning, everybody. This is Latin American Network of Matter Condensed Physics and Material Science. Today we have a special speaker who is Dr. Kunduz Turekhanova. She is from the Al-Farabi Kazakh National University, Kazajistán. El día de hoy tenemos una invitada muy especial que es la doctora Kunduz Turekhanova. Ella es de la Universidad Nacional de Al-Farabi en Kazajistán. La doctora Kunduz, ella estudió su pregrado y maestría y doctorado en la Universidad Al-Farabi, Nacional Al-Farabi en Kazajistán. Es profesora también en esa universidad de física, ella estudió física, y también ha hecho una estancia en la Universidad de Cambridge el año pasado, gracias al financiamiento del Bolachak, que es un programa programa de Kazajistán. Ella lidera grupos de investigación en la Universidad de Al-Farabi, en Kazajistán, y está dispuesta a tener colaboración con universidades en el mundo, en Latinoamérica inclusive. Bien, Dr. Kunduz Turekhanova, she studied physics in the Al-Farabi Kazakh National University, also mastery and doctorate, and she's a professor there. Last year, he has been at the University of Cambridge in the Cavendish Laboratory, thanks to the Bolachak program from the Kazakhstan. She's one of the top researchers in Kazakhstan. She's based in Almaty and is very eager to collaborate with researchers around the world and researchers from Latin America as well. The Latin American Network of Matter Condensed Physics and Material Science is a network including different universities in Latin America. In the University of San Marcos in Lima, Peru, National University of Colombia in Bogotá, in Colombia, Mayor University of San Andrés in Bolivia, Instituto Atómico de Bariloche in Argentina, Catholic University of North in Antofagasta in Chile, University of San Sebastián in Chile, Federal Rural University of Rio de Janeiro in Rio de Janeiro in Brazil, University of Pernambuco in Brazil, University Fluminense in Brazil as well. The Simbestap in Mexico, and University of Oriente in Venezuela, also el Centro de Investigaciones de IBIC de Venezuela, and University of Córdoba in Argentina. Well, this is our network, and vamos entonces a dar la bienvenida a Kunduz y para que empiece su charla ahora. Ella va a dar una charla acerca de los magnetocaloric coupling in Terbium Tantalate. Welcome, Kunduz, and you can start your talk now.
Thank you so much. My great appreciation for your invitation for your Latin American seminars. I'm proud to participate on this seminar. And now let's introduce my report, Magnetic Coupling of Terbium Tantalate, which this research was done in the Cambridge University. You see that on this slide, all of the authors which we together research this investigation of the terbium tantalate at the Cavendish laboratory. Here also my scientific supervisor, Siddharth Saxena, and you know that as introduced the Professor Louise, that I also use the Bolashak program, which is supported by our Ministry of Education, Kazakhstan, and magnetic coupling of terbium tantalate. And of course, here you know that the in diamond lattice have the mainly focus on the ceramic materials, including magnetic S-side spinels. And here, no, next. On this work, we expand the prairie rock, this Kelly Jan Pearson third Pontis, and focused on the nuclear and the magnetic structure terbium tantalate at the variable temperature and the magnetic fields using the powder neutron diffraction. Here at 1.2 Kelvin below the temperature, and the slight increase and the angle distortion and the band distortion is observed from the 0 to 6 Tesla. And we interpret this as an anti-paramagnetic ordering, triggering magnetic elastic coupling terbium tantalate. Our variable temperature and the field magnetic sustainability and the specific heat measurements allow us to attract changes in the magnetism. And from these measurements, the Neal temperature is found to the surprised by the magnetic field, and the transition to content antiparamagnetic state is observed applications the field. And on this picture, you see that the polycrystalline terbium tantalate was synthesized according to the solid state ceramic reaction, as has been in the experiment we told get on this powders was firstly heated at the 800 Celsius overnight to remove moisture, and of course, on the Cavendish laboratory, you used the powder X-ray diffraction, which was carried out at the room temperature on the Bruker diffractometer, and we also read field refinements we carried out using the Topaz program with the Chebyshev polynomial background and the Thomson Cox Hastings pseudo Poigat peak shape. And here you see the structure of terbium tantalate has been previously reported to be monoclinic Ferguson space group 15, and you see that the figure shows the crystal structure, monocrystal structure of terbium tantalate, and the here A, B, C axis represents the directions of the unit cell in the 3 dimensions. For example, on the panel A, view along the axis A, that the B axis is pointing to the right, green arrow, and the C axis is pointing upwards, blue arrow. Here, this one. And this means that the viewer is looking along the A axis. And approximately in accordance of this, and we also on the panel B, we see that you are looking along the C axis, you see that AB plan of the structure. And the panel C, terbium sublattice only, this shows that the terbium atoms, blue spheres with their connectivity, and the A axis pointing upward, and the B axis to the left. This means the spinel highlights the terbium atomic network within the unit cell. And red field refinements, the room temperature peak XID of terbium tantalate is shown in the second next picture on this on this picture. You see that here room temperature PXAD of for terbium tantalate. Here means that red dots experimental date, and the black line calculated intensities, and the green line difference pattern, blue thick marks Bragg deflection positions. And here also that the unit cell parameters as the terbium and the tantalate atomic positions were refined, while the atomic positions of the oxide ions were fixed based on the neutron diffraction date from previous experimentals. And using all of this date, first of all, we examine the magnetic sustainability. Here, for example, magnetic susceptibility. You see that magnetic susceptibility is approximately equal to the ratio of magnetization to magnetic field, and on this graphic, you see that this figure shows the temperature dependence of the magnetic susceptibility plotted as a ratio magnetization to the magnetic field in EMU Oersted mole mines and measured under the different magnetic fields. Ranging from 0.01 and until 1.2 Tesla. And as the temperature decreases, you see that the ratio magnetization and the magnetic field increases. First, abroad around the 3, you see that 3 Kelvin, around 5 or Kelvin, depending on the field, and then decreases again. The broad peak in indicative of short-range magnetic correlations or magnetic transitions. And this zoomed view of this scale of this graphic at low temperature region between, you see that between 1.5 until the 3.5 Kelvin, showing a clear separation of the curves for different fields. At high magnetic fields, red curves, and the maximum ratio means the magnetization to the magnetic field shifts slightly and is less pronounced. And these features suggest that field-dependent suppressions of magnetic ordering and are typical for systems with competing interactions, spin glass behavior, or low dimensional magnetization. And after it, we found the derivative of the product, the magnetic susceptibility with respect to the temperature derivative temperature. Next. This one, we differentiated, and as a function of the temperature as the selected fields are shown the previous, and you see that for example, here they are given the mean of magnetic fields, and you see at 0.01 Tesla, a sharp lamp type feature is observed at 2.25, this one, here 25, and which corresponds to the nil temperature. This indicates the onset of three-dimensional antiferromagnetic ordering. Additional, another shoulder-like feature is visible 2.0 Kelvin, which is donated as a this one, donated TN2. And the second transition suggests a more complex magnetic structure, such as multiple antiferromagnetic sublattices or competing interactions, decreases from the 2.25 to the 2.05. And 5. And here you see that on this, if we this picture plot peak of the temperature, the plot shows the magnetic phase diagram in the field of temperature BT. Here, magnetic field independence of temperature space based on evolution of two magnetic transitions. And as the transition temperature were extracted from peaks in the temperature of derivative of magnetic susceptibility, as seen in earlier panels. The The blue curve here represents, and it's the first magnetic transition, in higher transitions, in higher temperature transitions, and the brown curve corresponds to the second magnetic transition, the low temperature transitions, this one here. And the both transition lines shows that the decreasing trend with increasing magnetic field, which suggests that applied magnetic field suppresses the magnetic ordering, and the second magnetic transition vanishes above here, for example, above the 0.3 Tesla, indicating that this lower temperature phase in the particle and the magnetic field. And for first magnetic transitions, the temperature persists up 0.4 on this stats, and beyond it also shifts ground significantly. And this phase diagram indicates the field induces suppression of anti-magnetic phases, helps identify boundaries between magnetically ordered and the disordered ferromagnetic states. And after it, we researched the isosomal magnetization at different selected temperature, as shown on this figure. And below the higher Neal temperature, the isosomal magnetization exhibitions as characteristic shape coach insert, and it's the zoom version of this on this region between 0 and 1 Tesla. 1 Tesla. And here magnetization in units of Bohr magnets per formula, and the B is the external magnetic field in Tesla on this diagram. And at low temperature, for example, you see that between 1.8 and 2. Maybe is this one between on this region, dark blue to pink curves, the magnetization increases rapidly with field saturated around the 7, just more than 6 Bohr on this parameter and isosomal magnetizations, and indicating ferromagnetic-like behavior with the spontaneous alignment of magnetic moments. As the temperature increases above 4, above, for example, here is 3 or 4, the green, for example, liner to saturation behavior gradually disappears, and the magnetization becomes more linear. This more linear, and the applied field characteristic of paramagnetic behavior, and the insert highlights the low field region up to 1 Tesla with the initial slope curves is noticeably larger at low temperature, again indicates strong magnetic interactions and the presence of magnetic ordering. This overall trend suggests that a field induced transition from the paramagnetic to an ordered magnetic state, or presence of spontaneous ordering at low temperature, which weakness and vanishes with the thermal fluctuations. And the differential magnetization as a function of applied magnetic field, and we know here isosomal magnetization of different temperature, and as this means that here the isosomal magnetization magnetic phase analysis. This composite figure illustrates isosomal magnetization behavior of the material at the various temperature. You see that from 1.8 Kelvin until the 100 Kelvin. And how it evolves into the magnetic phase diagram via differentiation and the peak analysis. And the isosomal magnetization curve, the main this one, you see that just only we zoomed until between 0 and 1.6 Tesla, we anti-magnetic feature surprised with increasing temp, and when we differentiated, and you show that the main plot shows they measured from the focuses on the field of 0.6, showing that how initial slope of dependence magnetic field changes with temperature, and as the antiferromagnetic like feature non-linear step increase becomes suppressed as the temperature increasing and consisting with the weakening of antiparamagnetic order. And here you see that the differential curves by numbering differentiating by the intensity of magnetic field, you see that curves reveal peak structure at low temperature. Peak structure, and these peaks correspond to the characteristic field which decreases with increasing temperature. From you see that from 0.33 magnetic field Tesla for example, it is where the temperature was 1.8 Kelvin, 8 Kelvin in this bin, and the near the at the temperature 2.2 Kelvin, here the magnetic field 0.1 Tesla. Here you see that, and the red dashed arrows tracks the peak field shift, trace the magnetic phase boundary. And here the top right panel, magnetic phase diagram, and the magnetic phase diagram is constructed by plotting the peak positions from this date as a function of temperature. And it shows that a clear downward trend indicating that field required to induce the transition decreases with increasing temperature. And as a phase boundary temperature near 2.25 above which the antiferromagnetic order vanishes. And in conclusion, is a figure comprehensively demonstrated how the antiferromagnetic like ordering is suppressed by the both temperature and the magnetic field, and the differentiation of isosomal reveals precise field scales of transition. A field temperature based boundary can be extracting from the evolving peak position. And next slide, on this slide, they are given the results of the specific heat at different fields, magnetic different fields. And you know that the magnetic specific heat of the terbium tantalate at selected fields is a and at nil temperature, a sharp peak was observed. This corresponds and the 3D antiferromagnetic ordering in the different state of magnetic susceptibility on the temperature plot. On application of magnetic fields, the peak decreases in temperature and it becomes border differing from the magnetic susceptibility and the isosomal magnetization measurements. The second nil temperature wasn't seen. The heat capacity date possibly due to the change in magnetic entropy being the too small detect and the insufficient temperature steps resulting the merger of nil temperature first and the second nil temperature. And this you see that this figure represents that the temperature dependence of magnetic specific heat divided by the temperature temperature measured at different external magnetic field. The date is used, they extract the magnetic transition temperature and they construct a field temperature phase diagram. And if you plot peak temp, for example, this diagram, magnetic phase diagram from the heat peaks. This one, you see that the peak temperature existed from each curve in the left panel and plotted against the corresponding field values to construct magnetic phase boundary. And as a resulting curve shows a clear downward trend, demonstrating that transition temperature decreases with increasing fields. And the boundary vanishes around 2.25 and at 0 Tesla, at the zero magnetic field, you see that the temperature around 2.25 Kelvin, and the collapses, for example, that at 0.8 Tesla magnetic field, the temperature approximately 2.2 Kelvin, consistent with the critical field suppressing the transition. And summary the evolution of specific heat at different fields on the dependence temperature. Peaks reveals a second order of magnetic transitions, likely antiferromagnetic, and the magnetic field suppresses this transition in continuous monotonic manner, and as a constructed phase diagram provides the critical field in the dependence temperature relationship, important for understanding the stability of the ordered phase. And discussion the phase diagram, the magnetic behavior has been previously discussed with a reference diamond lattice of Tiberium ions described by the nearest neighboring interactions, and the nearest neighboring interactions second. And here now it means that quantum ferric materials with the spin and the charge degrees of freedom couple of at low temperature, promising area for discovering novel quantum phases. Experimental study of such phenomenon is limited by lack of model materials, where the magnetism and the dielectric properties can be turned using the magnetic field at low temperature. In a recent breakthrough, we found the terbium tantalate exhibits enhancement in dielectric response application of magnetic field, indicating magnetoelectric coupling. These measurements were conducted on the both polycrystalline and the single crystalline terbium tantalate. And on this picture, you see that a single tetrahedral structure of diamond lattice, and where the D1 and the D2, it is the distance between the nearest neighboring atoms, and C is the angle, angle phi, it's the angle, but here, if it's Fc is the angle between bonds, and the bond distortion and the angle distortion indexes dA calculated from the using the D sub 2 and the D sub 1 and the C. And on the this picture, and you see that it is as this the distances as a function of magnetic field collected at the 20 Kelvin and 1.5 6 Kelvin, and here this they are given for different temperature, and from you see that from the read field refinement of P and they collected at length and 2.45 angstrom. And this means that on this research, we investigated terbium tantalate using the magnetometry and the heat capacity and the neutron diffraction revealing three-dimensional antiferromagnetic ordering at nil temperature 2.25 Kelvin, conformed by sharp transitions in derivative of the magnetic susceptibility and the magnetic derivative of the magnetization by the intensity of magnetic field and the specific heat. We found the terbium ions from the stretch diamond lattice, which undergoes increased bond and the angle distortions under the magnetic field at 1.6 Kelvin, suggesting quantum magnetoelectric coupling. With increasing field, the system transitions from antiferromagnetic to counter antiferromagnetic and eventually to paramagnetic order. And these findings highlight the interplay between magnetic ordering and the lattice distortion in terbium tantalate, offering new insights into the quantum magnetic electric effects in the rare earth tantalates. And that's all. Thank you so much for your attention. It's a picture of our lovely city, Almaty. That's all. If do you have questions, please welcome.
Okay, thank you very much, Kunduz, for your nice talk and very nice photo of Almaty. That is the former capital of Kazakhstan. Well, now it is time for the questions. Can you activate your camera, please, Kunduz? Okay, now it's now time for the questions. We have many panelists and also invited panelists. First, we are going to start with some Latin Americans. Let's go to Argentina, who Professor Gabriela Grad. Gabriela, you have questions?
Hello, Kunduz.
Hello.
Very, very nice talk and very interesting topic, but no, I don't have questions today.
Okay, thank you, Gabriela Grad from Argentina. Let's go for it. Professor Sergio Conejero from Católica University of Norte Católica University in Chile.
Here I am. Hello to everyone. Hello, Kunduz. Thank you very much for your presentation. Regrettably, I entered a little bit late because I had some problems with my internet connection. So probably you explained the question that I'm going to ask you at the very beginning, but I have some question related to the nature of the compound. In this case, you are seeing this magnetoelectric coupling phenomena with terbium, but do you have this kind of similar behavior with other lanthanides like europium, like europium? I don't remember. I'm forgetting the rare elements. But you can see the same behavior with other rare earth elements.
For example, the rare earth tantalates and the lanthanide tantalate have attracted increasing such as phosphorus and the somal barriers and the skin tolerates and the dielectric ceramics And I think that more magnetic studies have been done of the isostructural naivates and the lanthanide tantalate. And we, of course, on this work, we expanded the work of the Kelly and the Yan and focused on the nucleus of magnetic structure. Before, of course, it's lanthanide, tantalite was researched similar on these methods.
Oh, okay. So I have another question related to the experiment. I suppose these are bulk experiments, right? Have you tried with thin films experiments? Because I have read that you can modulate the magnetoelectric coupling via a strain.
All the data which are given on this presentation was done experimentally in the Cavendish laboratory, and the polycrystalline, for example, terbium tantalate was synthesized according to the solid slate ceramic reaction, as has been reported elsewhere. And here we, for example, on the we use the quantity 50-50 molar amounts of the reagents were thoroughly mixed at the agent pestle and the mortar and pressed into the I think that the size of pellet maybe 6 or 7 millimeter and placed on the aluminum crucible. And we also, of course, used on the Cavendish laboratory powder X-ray diffractions. And the PMC on the Cavendish laboratory Maxwell quantum design PPMS. The heat capacity of the terbium tantalate was measured on the quantum design PPMS between 1.8 Kelvin until the 30 Kelvin, and the different magnetic fields ranging between 0 Oersted until 70,000 Oersted. And the sample was mixed and the equal mass of this all of this which constructed this not this all of this date of was get from the experimental work.
Okay, yes, I understand that. I understand better now how you just carry out a solid state reaction. But have you tried to reduce dimensionality using other kind of experiments, trying to obtain thin films or nanoparticles, for instance?
Now we are planning to expand all this all of these experimental dates for this SEM.
Yeah, because it would be particularly interesting trying to form thin films, because you can modulate the properties using a strain. You can modulate or tune the magnetoelectric properties using a strain. I don't know how difficult is that, but that would be interesting. And my last question, what are you planning for future? I think you just commented that probably you are going to try other kind of experiments, trying to reduce dimensionality, but what other elements are you planning to use in future? Other elements like europium or other kind of rare earth elements?
Of course, my how can I say, our interested plan will be connected with our country, Kazakhstan. Unfortunately, we haven't this such equipments which Cavendish laboratory have, but now we would like to construct maybe the by hand to construct the where we can measure the magnetic fields by the temperature using helium and now we are planning it. And you know that our Kazakhstan country has how can I say, well, is a rich country which have more nature materials, which would like to investigate in future, which can be used in industry in our country. Okay. Is this our plans and our wishes?
Okay, thank you very much for being here, sharing your work.
Yes, thank you so much.
Nice presentation.
Thank you.
Thank you very much, Professor Sergio Conejeros from the Catholic Northern University in Chile. Now, let's move to Peru with Professor Henry Moncada. Henry Moncada.
Hola,
Your camera, please.
¿You listen?
Your
Yes.
camera, please.
Camera. Camera. Okay, hold on. Okay, now. Hi. Nice presentation. Very nice. Even though your research is out of my field, and so I will ask my question in the name of all the people that basically barely understand what you do. So you mentioned the change of the magnetic field with the temperature. So my question is going to the, in the point, what you can do with that. I mean, what new technologies you can develop with the research you are doing. For example, yesterday I watched a video about China develop a speed train, that use kind of magnetic devices to basically lower the rugosity and increase the speed of the trains. So, what things you can develop with the research you are doing? What devices you can construct in terms of new technology, for example?
New technologies. Honestly, I saw that the last new technologies which can best investigated such properties in Cavendish, of course. For example, the equipment is a quantum design, PPMs, but it was the price of this equipment is so highly, and unfortunately we haven't in our country. But now, last time after departure from the Cambridge, recently, of course, I'm in Almaty, and how can I say? I noticed that our government changes the politics and have more new programs. One of them, for example, our Al-Farabi University has a joint program with the China universities. Yes, China universities. And for example, in our faculty, we have the branch of the Chinese North technological universities. But of course, honestly, I haven't enough time to research, maybe to introduce all the programs. But I think that in future we can expand on the international label. For example, just only I read, of course, it's not connected with our this research, but for example, the research center by the astrophysical center is planning to open in our Farabi University with supporting was this China University.
Well, thank you, brother. And nice to meet you.
Thank you so much, Hannah, for your question. And okay.
Thank you, Henry Moncada. Kunduz, I think that the question of Henry Moncada was more related with the possible applications of this sample. Yeah.
Possible application, and the user knows that as I mean, in our country, unfortunately now, how can I say, our country consists as a rare maybe country, but we would like to transform to the producing some new technologies as a maybe where new materials, we are using the best quantities with the superconductivity and the thermal conductivity, and using, of course, for example, one of technologies we in our government we use the in agriculture field also is a field of one of examples, and one of course it's connects with the new materials which can be used in the industry.
Okay, nice. Thank you, Kunduz. Now let's move with the next panelist. You know him maybe. It is Professor Stuart Holmes. He's from the Cavendish Laboratory and also from the University College London in UK. Stuart Holmes.
Kunduz, thank you for your presentation today. Very interesting. My questions have already been asked by Sergio and Henry, so I'll change the questions. If you have a single crystal, you mentioned that some of your materials are single crystal. Does it matter which orientation you use for the magnetic field? If it turns out that there is this anisotropy, that might give a hint to making thin films, straining them in the way that Sergio asked. Do you see a dependence on field orientation?
Yeah, of course. Here we orientations we also accepted this investigator with the sure we include the orientation of the magnetic field. Here was the first field, and I think in the, as you say, that as seen film, we can use all these results which are doing. Of course, now it's not the last result. Now we are planning to expand and this investigation on other form, and this crystalline structure, and yeah.
Thank you. I have one further question. You showed a very small change in temperature between your data points.
Yeah.
Experimentally, is it easy to set that small difference between the temperature?
Not. I think that, for example, one experiment we repeated at least maybe 10. I think that we're getting it. Sometimes we spent more than 2 months. Sometimes.
Yes, it's a lot of data points. It's maybe 10 millikelvin between the data points.
Yeah, and I think that I spent 1 year, and for the getting, it's not my just as I say that it's not my own results. It's results of the team work.
Yes,
with the researchers from Cavendish Laboratory, and the supervision you see that Saxena, and that way we repeated all of it. Experiment with the PhD students and the other researchers from other universities. Maybe you know that Matt Koch, and from the Birmingham universities, and
I see, Birmingham. Yes, very nice. Thank you again for your talk. Very interesting. Thank you.
Thank you.
Thank you, Stuart Holmes from the Cavendish Lab and University College London. Well, Kunduz, we have many Kazakh inviters here. For example, we have Kanat here. Kanat, do you have any question? Your camera, please, and your microphone. Kanat.
Hi. Kunduz, thank you for a very interesting topic. After the questions of the colleagues from the American, I have no questions. Thank you. Very interesting.
Okay, thank you, Kanat. Maybe Jumat Kargin. Jumat, your microphone, your camera.
Hi, colleagues, once again. Also, from my side, thank you very much, Kunduz, for a very interesting presentation. I think that it's a very big job you have completed. So my first question is, usually for obtaining some of the dependencies of scientists doing and three experiments where we in dynamic we can show what are the one parameter depends on the other. Here we completed 15 different 15 experiments with different 15 magnetic fields. So what is the reason? Because I think you spent a lot of time. What is the reason?
First of all, our goal, we would like to investigate at the low temperature. In that way, we repeated and we get investigated this at low temperature, the diamond-like lattices. Terbium Tantalate.
Okay, you're very happy. You have a lot of time for doing that experiment. Okay, and to come back, the question was put you, Dr. from Chile, Sergio, and Dr. Stuart Holmes. So about anisotropy. So as I understood, you have deal with the bulk samples, yes?
Yes.
Which was sintered by common ceramic methods. But in common, when we measure the magnetic fields, magnetic properties, the samples basically has anisotropy of the magnetic fields. Does it mean that you not focused on the anisotropy studied these samples, or if you not, what's the reason? Because anisotropy is very crucial for magnetic properties, because some bulk samples, they have different diamagnetic factors we need to take in account. What's the reason?
Phase diagrams, and this means that at low temperature the diagram of the elements is changed, and as you see on this here, the nil temperature, this first between when we investigated the in the region different temperature, we found the special temperature around 2.5. I explained here. We found that the interesting phenomenon that magnetic success here, that
Okay, thank you. And my last question,
Phase
for
diagram
this
that,
study,
yeah.
for this
You see
study,
that, magnetic field, for example, is increased, decreased at approximately 0 Tesla at the approximate temperature 2.25 or 5 Kelvin. And find the magnetic phase diagram.
okay, thank you. And my last question, so as I understood you, all this investigation of magnetic properties of terbium tantalate samples, you have provided also, you carried out by measuring of the heat capacity, yeah?
Yeah.
But I didn't catch you. What was the reason? Because the magnetic field and capacity measurement is quite different measurements. Why you need to provide additional measurement of that materials?
And you know that, for example, it's the in industry, not only the magnetic properties plays important role, and the heat thermal also properties also plays important role. In that way, we also decided to investigate the heat capacity of the materials, and they are given that it's not here the heat capacity ratio by the temperature they are given. And after
Okay.
it, you see that the magnetic field decreases with increasing temperature. We see that.
Okay. Could you say that measurement of your measuring of the heat capacity finally give you additional information about some of the ordering of atoms inside of your materials, with your samples?
Yeah. Sure. Yes.
Okay, thank you very much. Good job. Thank you.
Thank you.
Okay, thank you very much, Yumat Kargin from the Astana in Kazakhstan. Well, let's go with Timur Khan. You have any question? Your camera, please. We cannot hear you, Timur Khan.
And I would like express special thanks to Kunduz. And I'm very about Kunduz. Can you share if any what are major scientific groups in the world which work in the same field on the same subject? May you stay in a cooperation with them, or may you know what they do, and just may you express your vision.
Yes, I can share with our work, maybe a link I sent you. I'll send you the Luis, and maybe our some thesis or some articles I can send to you.
Okay. Okay. Thank you, Timur Khan. Well, I think that we have finished with all the panelists. Just very short question from my side, Kunduz. One of the first plots that you showed is about the susceptibility with temperature, right? You measured that in the Cavendish lab, right?
Yeah, yeah. All of these results was done was get in Cavendish laboratory. Yeah.
Yeah. The previous one, I think. Yeah. No, that is the derivative. The previous one.
This one.
Yeah, that one. That is in the PPMS or MPMS?
PPMS.
Yeah, it is in zero field cooling or field cooling?
Field cooling. Mhm.
Okay. Yeah, you would decrease it with a free apply field. Okay. Nice, excellent. That is good. Okay, very good. Let's see if there is question from the public. Okay, let's move with Ximena Velázquez to see if there are questions from the public in Colombia and Latin America.
Good morning, Professor Luis. No, we don't have any questions from our networks. In this moment, the people will say thank you for this incredible conference. Thank you.
Okay, many greetings to you from the Latin American public, Kunduz. What about from Peru? Maybe the Peruvian public, James Goroy, Melvin.
Oh, bueno, saludos, saludos. No tenemos pregunta, profesor, solo saludos por la presentación de la doctora.
The Peruvians send you many greetings, Kunduz, and they enjoyed the talk. Okay, well, thank you very much. Kunduz, could you stop sharing your screen, please, because we want to see a very nice photo of the. You took the photo?
Hi, no. All of you, I invite you to visit our Almaty city, which is ex-capital of our Kazakhstan country, which is located near the mountain. As you see, that surrounded by mountain. In that way, welcome in future. If you plan to visit our country, I can meet you, and we can also connect with me. We are waiting you, all of you. Thank you so much for your attention, for your interesting questions. And I think that in future we can maybe collaborate, we connected with some research works. Thank you, all of you.
Could you stop showing your screen? And because
okay.
the other panelists would like to say, open your camera, please, everybody, to say goodbye to Kunduz. And your microphones as well, to say goodbye to Kunduz. Okay. Kanat?
Bye.
Thank you.
Bye.
Bye.
Thank you, Kunduz. Goodbye.
Bye.
And ciao, ciao.
Chao.
Cortar transmisión, Jimena.
Bye.
Bye.